Hello students, welcome back to my channel JPPHYSICS. In today's lecture, we are going to derive the expression for law of conservation of angular momentum. This question is frequently and repeatedly asked in your previously year's question, that is state and prove the law of conservation of angular momentum. Okay, so let us see what will be the proof of this law of conservation of angular momentum. First, you have to write the statement for this law. What is the statement for this law? That is, if there is a no any torque acting on the body, that is tau is equal to 0, no any torque acting on the body, then its angular momentum remains conserved or its angular moment remains constant. We have to prove this law. Okay, for this proof, first we have to write the expression for angular momentum. We know that expression. What is that expression for angular momentum? It is nothing but L bar is equal to R bar cross P bar, where L is angular momentum, R is the position vector from the axis of rotation, and P bar is nothing but linear momentum. What is linear momentum? We know that expression for linear momentum, mass into velocity, right? So now we have to prove that if there is no any external torque acting on the body, no any external torque, already we know that this tau torque and relation between the force, right? That is tau is equal to R bar cross F bar. And to bring that formula or to derive that formula and to prove this, we have to differentiate this equation on both sides. So what will be the differentiation with respect to time? Okay, so I will differentiate this. dl bar by dt is equal to this differentiation of multiplication. What we will do? First term will be as it is, that is R bar will be as it is, into differentiation of second, that is dp bar upon dt, right? Plus what will be second term will be as it is, and differentiation of first, that is dr bar by dt. Now put this dp bar by dt as it is, plus this p bar. What is p bar? It is nothing but mass into velocity. So what I can write? Mass into v bar into dr bar by dt. What is this? This is nothing but rate of change of displacement, that is velocity. Therefore, that will be v bar. Now, r bar cross. What is this dp bar by dt? dp bar by dt, that is, this is linear momentum. Rate of change of linear momentum is nothing but the force. We know that. If I put this value, see, d dt of mv, correct? So, mass is constant. dv by dt. What is dv by dt? It is acceleration. That is mass into acceleration. What is this? This is nothing but force. F is equal to ma. Second law of motion. Newton's second law of motion. Rate of change of momentum. Linear momentum. Means this is nothing but the force. Therefore, R bar cross F bar here. Plus, see, here there is a cross multiplication between V bar and V bar. Means cross multiplication between, of vector with itself. V bar cross V bar, that quantity will become 0. That is cross product of any vector with itself is equal to 0. You know this law, correct? So V bar cross V bar will become 0. Therefore, this whole term becomes 0. dl bar by dt is equal to what? R bar cross F bar. And we know this relation. What is this relation? This is nothing but the torque acting on the body. Means R bar cross F bar is nothing but tau bar. That is torque acting on the body. dl bar by dt. Now, if you see this relation, what it shows, if this tau is equal to 0, that is no torque is there, it means that this L is constant. L means angular momentum is constant, because the differentiation of constant term is equal to 0. Correct? We have taken this tau is equal to 0. It is happen when this L is constant. Hence the proof. We have to prove this only. See what I have told you, the statement. If there is no any torque, no any external torque acting on the body, its angular momentum remains constant or its angular momentum get conserved. This is the proof, only this proof. You will get 3 marks for this, but you have to write the statement first and then you have to write the formula for angular momentum, differentiate that terms, you will get the result. That is, if no any torque, that is tau is equal to 0, then L will be constant. You got this derivation? We are going to another derivation. We are going to do another derivation, that is kinetic energy of rolling body. From this rotational dynamics, this last derivation I am going to do, important derivations. Besides this, there are another derivations also, that is kinetic energy of rolling body, and also formula for angular momentum, that is L is equal to R bar cross P bar. 2 marks derivations are there. Sometimes it can be asked for 3 marks also. If you have any doubt or if you want that derivations also, you comment me in comment box, then I will solve or I will do that derivations also. But today I am going to do the derivation, that is kinetic energy of rolling body, because this derivation is asked for many times. Okay, so let's do that derivation, that is kinetic energy of rolling body. Kinetic energy of rolling body. See, kinetic energy of rolling body means one body is there, it is rolling without slipping, or it is rolling simply on a horizontal surface. At that time, it is making translational motion and also rotational motion like this. See, this body is rolling, correct? This is rotating about its own axis, and also it is moving in a straight line, means it is performing translational motion also. Means when we consider the rolling body, at that time we have to consider translational kinetic energy and also rotational kinetic energy. Means when we have to derive the kinetic energy of rolling body, we have to add both these kinetic energies, that is translational kinetic energy and rotational kinetic energy. So when we are going to do the derivation, first you have to write all that things. Let us consider one body of mass m rolling about an axis. At that time it is making rotational motion and also translational motion. Let v be the velocity of the body. Okay, so all that things you have to write first, and then you are going to derive the expression. For that derivation, that is kinetic energy of rolling body is equal to kinetic energy of translational motion. I will write it as a T, and kinetic energy, that is rotational kinetic energy, that is kinetic energy R. Okay, put the value. Kinetic, translational kinetic energy. What is the formula for translational kinetic energy? It is nothing but 1/2 mv square. If v is the velocity, m is the mass of the body, then what is the formula for kinetic energy? It is 1/2 mv square plus kinetic energy of rotating body, that is rotational kinetic energy. We know that formula, rotational kinetic energy. See, if you are considering the translational motion and rotational motion, by analogy, when you consider in translational motion, there will be mass. If you want to remember that formula, you can remember like this also. See, if you are considering mass in translational motion, that time there will be inertia in rotational motion. If you are considering velocity, that is linear velocity in translational motion, you are going to consider angular velocity in rotational motion. So this formula will become 1/2. In place of m, there will be I. In place of that v, there will be omega, that is angular velocity. Mass, inertia, and this velocity, linear velocity, here there will be angular velocity. Now if k is the radius of gyration, I can change this formula like this. See, 1/2 mv square plus 1/2. What is this value of I, moment of inertia, in terms of radius of gyration? We know that. What is that value? It is mk square. Means in place of this moment of inertia, you have to place mk square. See, we know which type of body is here. Means if there is a sphere or there is a rod or solid sphere or hollow sphere, we don't know that, correct? So here we are not going to take that particular inertia. We will take radius of gyration, that is moment of inertia in terms of radius of gyration, that is mk square. So next, omega square as it is. Okay, so 1/2 mv square, right? In this v square, at place of this v square, what I can do, or put this v square as it is and put the value of this omega in terms of v. See how? mk square. What is omega? See, v is equal to r omega, right? So omega is equal to v by r, right? In place of omega, I will put the value of omega in terms of linear velocity, that is v upon r whole square. Then this formula will become 1/2 mv square, 1/2. This m I will write small m because I have taken here small m. So I have to write here also small m. Then here 1/2 mv square. Therefore, I will write mv square here. What remains? K square upon r square. K square upon r square. Here there is 1/2 mv square. Here also 1/2 mv square. Take common. Therefore, 1/2 mv square in bracket. Here only 1 will be there. And here k square upon r square. That is kinetic energy of rolling body is given by 1/2 mv square in bracket 1 plus k square upon r square. Also they can ask question like, prove that kinetic energy of rolling body is equal to 1/2 mv square in bracket 1 plus k square upon r square, or kinetic energy into 1 plus k square upon r square. They can ask the question like this also, or simply they can ask, derive the expression for kinetic energy of rolling body. For that you have to write initial all that information. That is, let us consider a body with mass m, rolling with some speed. You have to write all that things. Means linear velocity, let's consider as a v, angular velocity as omega, k is the radius of gyration, and we can write the kinetic energy of rolling body, that is sum of kinetic energy of translational motion and kinetic energy of rotational motion. Means rolling body or rolling motion is combination of rotational motion and translational motion. So you have to take both the kinetic energies, that is translational kinetic energy and rotational kinetic energy. Put the formula, make the substitutions, that is I is equal to mk square in terms of radius of gyration, formula for moment of inertia. Then again put the value of omega in terms of v and r, that is v by r whole square. If you derive that and take the common 1/2 mv square, you will get the final relation, that is kinetic energy of rolling body is equal to 1/2 mv square in bracket 1 plus k square upon r square. This is the required derivation of kinetic energy of rolling body. You understood both the derivations? If you understand that derivations, please like, share and subscribe my channel, and also press the bell icon so that you will get the notification for next video. In next video also I am going to do the important derivations from that next chapter, mechanical properties of fluids. But also if you have any doubt regarding rotational dynamics, you can ask me in comment box. Okay, thank you.